Okay, so we're going to start with topic 6.6, and this is the last part of the option B, quantum physics, atomic and nuclear physics, and this is the section on quantum physics. So this topic, this 6.6 is pretty neat. This is all about the nucleus. So this is nuclear physics. That's EAR, sorry. And if you think about that, there's the key word right there. So this is all about the nucleus of an atom. So how do they discover? We're going to go back and look at Rutherford and Geiger-Martin, the Rutherford scattering or the Geiger-Martin scattering experiment. And let's talk about this distance of closest approach. So you remember he shot alpha particles at the gold foil. So let's use that experiment. And this is going to be very exactly like what's in the textbook, but I think if you can hear it from me once and then if you can read it, then heck, that's pretty darn good. You're going to get a lot of this and you're going to understand it. So here, if we just say that we have an alpha particle, and alpha particle, as you know, has a plus 2 charge. But in the book, they call it a plus 2e charge. And we'll use that. And so it is going head on at the nucleus of a gold atom, so a much bigger gold atom, and it has a charge of Z times Z. If you remember Z in the nomenclature, not nomenclature, but just this, A, Z, and A minus Z was a number of neutrons, and A is a number of nucleons, and Z is a proton number. So Z times the charge of one proton would be that charge, and 2 times the charge of the protons in there would be the charge of this little particle, this alpha particle. So if it's going straight on at it, do you remember from the little tests that we took on 6.1 through 6.3? What's it going to do? It's going to bounce straight back. It's going to come straight back. It's not going to be deflected off at an angle theta. So, and then if you think about this, so if it goes right at it and gets as close as, let's just say right to there, and it stopped. It stopped right there because why? Well, this is positive and this is positive, so that's going to deflect it back at some point. I guess you could say as long as that is greater than 10 to the minus 15th meters, then that means a strong nuclear force is basically essentially not part of the forces that are acting on it, on these two particles, and so the Coulomb force would be in play here, and that would cause this alpha particle over here, this guy, I'm going to get rid of that, to actually be deflected back by the positive charge of the nucleus. Remember, we're not considering the electrons surrounding it at all. So let's go to the next page here and see what we got going on here. So if we say that it gets stopped right there at the as close as it can. Now, how close does it get? Well, that's dependent upon how fast it's going. If it's going super, super fast, I don't know what super, super fast is, but let's just say an appreciable amount of the speed of light, then it can maybe get pretty darn close and maybe even hit it. But I don't know. But anyway, I'm just saying very fast. So if it's going really fast, it can get closer and closer and closer. But the closest it can get is to the radius of the nucleus. And ta-da! By doing a little bit of math, they can figure out how big the nucleus is. So if it doesn't have much speed, then it's not going to get very close and it's going to be repelled back. So let's just take a look at this. So if from a previous chapter that we did not cover, I'm going to first pull in something. The potential energy between two particles is K, Q, Q over R, where R is let's call it D. Let's call it D, okay, over D. And we did not cover this, but this is pretty simple. This is the potential that exists between two particles. And you remember the K was also given to you as 1 over 4 pi times the E sub 0. Okay, so you can, but K is Coulomb's constant. So if that's the potential between the two particles, and this right here, this is the alpha particle, and this is the gold nucleus. This is Au, that's gold, and this is the alpha particle, that's the helium nucleus. Then this is the potential that exists. So if this alpha particle is going at the gold, and it gets very close to it, but it gets stopped right here, so it's stopped, then all of its EK here became U here. Does that make sense? I think it does. And so we can say that therefore that E is equal to K, Q, Q over D. Now that D is what we're looking for. That's what we want to be, what we want to be part of. So let's rewrite that in terms of what we talked about. So therefore E equals K, and then we're going to put in 2e, right, for the charge of the little alpha particle, and e is just the charge. So in this case, it would be 2 protons, 1.6 times 10 to the minus 19 if you wished, and then times ze, and that's, remember, z is the number of protons in the gold nucleus, so that could be any nucleus. Just so you know, it doesn't have to be gold. And then that would be over d. See, so that's just that equation rewritten with those terms. And then to simplify it, as they did in the book, it's k 2z, I think. I think so. 2 times z. I need to just do that so I know it's a z. And then times e squared. All right, and that's all over d. So now, how could we figure out the chart? Think of the ways that they could talk to you about the alpha particle and how it could gain kinetic energy. So they could accelerate it across a potential, maybe let's say 5,000 volts. I'm just making this up to give you an example. So you accelerate an alpha particle across and across a potential difference. So you'd want to make this side positive. And so your electric field, your uniform electric field would be going like this, and maybe you'd have a little slit right here, and then the alpha particle gains kinetic energy. It goes through, and then now it has a speed v, and now you know that you could set that ek equal to, don't forget, that ek equals 1/2 mv squared, and so you have the mass of the alpha particle, which would be what? 2 neutrons and 2 protons, and then if you could, and then it has a +2 charge, so you can figure out the speed of it across there by, gosh, just doing E equals F on Q, and then you could actually do F equals ma. I'm talking too much, but I'll just stop right there. And then you could find the acceleration. If you knew the distance, you could find the velocity. Lotta. Okay, I'm going to go on. All right, I'm going to stop for just a minute, and then I'm going to pause this, and I'm going to set you up for the mass spectrometer. Okay, so here's the mass spectrometer. So what about the mass spectrometer? What do we need to do? Well, the first thing is this gave rise to the evidence for isotopes. Let's make sure we understand that. So how do they find isotopes? So they have to have some ions that are created. So you have an ion source, and write that right there. So some ion source. In other words, some source of these charged particles. So then what they were thinking about was how do we select out just the particles of a given velocity? Now let's think about that. We want to select out just the particles of a given velocity. Well, what they do is right here, these are collimating, and collimating just means they're getting them all to go in one direction. Collimating, I think. And so these slits will get them all going in one direction, but it doesn't mean they're going the same velocity. They're just going in the same direction. But check this out right here, this circled area. So here we have a magnetic field going into the page, and that means that a positive ion, so notice I have positive ions, would be deflected up to the top of the page. But then they created an electric field that's positive at the top, so that's going to push positive ions down. So notice that there's no deflection while it's in this little electric field and magnetic field setup. So, but what if you're going too slow? Well, let's take a look at that real quick. Just think about that. E equals F on Q, but so F therefore equals EQ. That's due to the electric field, right, on the particle Q. But also F magnetic equals QVB, and in this case sine theta drops out because it'll be at perpendicular, it'll be at sine 90. But take a look, you could set these two F's equal. We've done this before, and if you do that, you end up having EQ equals QVB, and then look what cancels out. The Q's cancel out, and you have that you would only get that the velocities would be that coming through would be equal to E over B. So if you set these equal, why don't you try it on your own? Then you have EQ equal QVB. And then the Q's cancel because it's the same charge. So you have V, the velocity of the particle, is equal to the E over B. So you know therefore you know if you know the electric field strength that you created and you know the magnetic field strength that you created, you actually know the velocity of the particles going into the mass spectrometer. Pretty cool. So, well, guess what happened? That once they send them into this region over here, I'm going to try to highlight this for you. Just a brief highlight. No, I'm not. I'm going to use just a different color, and I'll just use yellow. So this area right in here that I'm going to circle in yellow. Now the electric field is not present. So if the electric field is not present now the particles are going to be deflected in a circular path. Okay? So if that's the case, then why, when they put a photographic plate here, did some of the particles go at a tighter circle than the other? Because they're both going the same velocity, they're the same ions, so that means they're the same atom, but they had different masses. So let's, up here in this corner, let's look at something. What kind of motion is this right here? That's circular motion. So now we have, remember the electric field is not there, so we have F equal QVB again, but that F is causing circular motion. So if you recall, F equals mv squared over r, and then we can set these two F's equal, and it doesn't take much math to figure out that we have Q, I'll separate that, V, B equal mv squared over r, and now this V and one of these V's will cancel, leaving you with V, and now you have that R, let's solve for R, would equal mv over qb. So let's take a look at what I just wrote here. If m is the same, if v is the same, we know that's to be true because E over B, we know. We know Q is the same because they're all coming from the same ion source, and we know B. So what's the only thing that could cause them to hit at different places on the photographic plate? Well, it's the mass. So they found out that there were some atoms that had the same number of protons, same charge, but they had different masses, and that led them to the understanding that there were isotopes. So that is the mass spectrometer. So again, if you just listen to me carefully there, and then if you were to read through the section on the mass spectrometer, you'd have 1/3 of this chapter very well understood. Okay? That is it.